Hello world, this is Craig. Let's take a look at the serial and parallel I/O board, or the SPIO, and just so that people can get familiar with the board, what it does, and learn enough about the board so that they can get busy using it. So if we look at the schematic, we can break this down into four fundamental areas. This is the fingers of the bus over here on the left-hand side. From those we have the bus transceivers. We then have the serial port. We have the parallel port. The rest of this is really glue to get the board to work. So for example, for the glue, we've got the address selection. That's done with this dip switch right here. And there's a equality detector right above that. We also have an onboard homebrew port. That's done with this latch and this second bus transceiver. These are just a resistor network and some LEDs to show us what's going on with this onboard port. And then we have a connector for the onboard port, which is J5 over here. So let's look at the transceivers in a little bit more detail. We have two 74LS245s, and they're both wired so that they're always enabled and the direction is set. So we can see that they're both set so that the A equals B line is low, so the direction is always going to be from the B to the A side. This takes the address byte, the upper byte of the address from the bus, and it creates a buffered version of that. So A8 turns into buffered A8 or BA8. It also takes the handshaking lines that we need on board. So we have the IO not M, we have the not read, not write, the reset, the address latch enable, and the clock, and it buffers those continuously. So all of these signals over here, the buffered ones, these are always enabled. So they may be a logic low or logic 1, but they're always being driven. Now this transceiver down here, you can see it also has its output always enabled, but the direction of this transceiver is controlled by some of the onboard logic to control whether things are going from the address data bus that's connected to the backplane over to the buffered address data bus. So this chip then, this transceiver, is changing directions to either drive from the bus to the board or from the board back onto the bus. Okay, so those are all the transceivers. Now these addresses, the buffered A8 through the buffered A15, are used to decode this board. We can see this is our decoding circuit down here. We have the 74LS682, which is an equality detector. So when these 8 inputs match these 8 inputs, the P equals Q line will go down. And here that's called the board select, or not board select. There's a 5-position dip switch, or if you want, you can just put jumpers on those. And this dip switch chooses the mask for the upper 5 addresses. So we can see here coming in, we have the buffered A11 through the buffered A15, and those are compared to the equal A11 to equal A15 that we get from the switch. Now the 74LS682 has an internal pull-up resistor on the inputs. So if this switch is closed, we can see that it pulls that input low, but if that switch is open, this 682 actively pulls that up to a logic 1. So what that means is that any switch that is closed or any of these that are jumpered across will be a logic 0, and if it's allowed to float up to a logic 1, then it's going to mask to a logic 1. We also, with the 682, we make sure that we're in an I/O cycle, and we do that because, remember, this buffered IO not M tells us whether we're doing a I/O bus cycle or a memory bus cycle. And for an I/O, this is going to be logic 1. So we just directly compare that with logic 1. And so that must also be true in addition to the address. Okay, so if the address matches and we're in an I/O bus cycle, this board select line will go low. So as a quick example, if we have the switches set like they are on this board where the switch for A11 and A12 are closed, so those are going to be at 0. And then 13, 14, and 15 are open, so those are going to be logic 1. So that means that the base address on this board is E0. Now since there's 5 lines of the address used to decode the port address for this entire board, that means that the lower 3 are used to decode which devices on this board we're actually selecting. Okay, and when we're looking at those, we can look at each of the devices. We can see the 8251 uses 1 additional pin, and that's connected to the command or the data line. That's connected to A8. The 8255 uses 2 additional pins. That's A0 and A1, which are connected to A8 and A9. So since this uses 2 pins in the 8255, we can see that that requires 4 port addresses. The 8251 USART requires 2 addresses because it has A8 as either being low or high. This onboard homebrew I/O port requires 1 port address, and then this expansion port requires 1 port address. And we have the addresses spelled out here, that if it's a 0XX, it goes to the 8255. If it's a 10X, it goes to the 8251. If it's a 110, it goes to the user sandbox and the expansion port. And if it's a 111, it goes to the auxiliary I/O. All of this glue in the center, these OR gates and these inverters, are used in a brute force decoding of the address to create those 4 different port address spaces. And you can work your way through this, and I hope that they're fairly easy to understand. We can see that this signal right here goes low anytime that address 2 is 0, and it doesn't matter what address 0 or address 1 are. This line, for example, goes low whenever address 2 is at logic 1 and address 1 is at logic 0, and it doesn't matter what address bit 0 is. Okay, likewise, this address requires the last 3 to be 1, and then don't care, don't care. So you can go through and you can look at all this and see exactly when all of these will go low at the appropriate time. Then there's 2 of them that are completely decoded. This is the read of the 111, which is the onboard homebrew port, and this is the write for the 111, which is the homemade port. There's also, for the interrupts that go to the backplane, a little patch area here that takes the signals that are going to the backplane, and it has some onboard signals that you can choose from. You can choose like the read ready or the transmit empty or the transmit ready from the USART. Here's a little OR gate that's connected to that in case you want to OR some of these together. And another thing to note is that on the sandbox expansion port, all of the unused gates, there's a couple of OR gates and a couple of inverters, are brought out to this header so that you can just use those on your offboard prototype area. Finally, there's one last little bit over here, and this is the oscillator that is used for the baud rate. So you can see we start with a 4.9152 megahertz oscillator. We have a little 74 LS393, which is a dual quad counter. So this has an effect of taking the 4.9152 megahertz signal and dividing that down by 256. So that gives us a signal that is 1.92 kilohertz. That signal goes into our USART. Our USART then internally has a divider for that. So if we just set our divider to 1, that means the baud rate for this USART is going to be 19.2 kilobaud. We can use that divider to drop this down to 1200 baud or 300 baud. If we want other baud rates, we can use either a different crystal, or we've left out some jumpers here that are normally shorted. There's some little surface mount jumpers on the back that you would have to cut those, and then you could patch this so that you can get this counter to divide by another value and get it to reset when you want. So you can pick any baud rate you want, but those are the 3 that you get with software control, either the 19.2, the 1200, or the 300. This device is the MAX 232 that converts all the TTL signals up to RS-232 plus or minus 12 volt signals. Now there are a couple of things to note about this board. If you are working on it, there's some things that are important to note. The first is that in order for the USART to work, it has to have the clear to send jump back to the request to send. That's done with JP4, and so to get this board to work, you have to have the jumper 2, 3 inserted into JP4. However, if you have a device out here that is actually using those hardware handshaking signals, then that's great. But to use it without those hardware handshaking signals, you have to have that jumper in. The other thing to note is that this board uses the reset on the backplane, and that reset didn't come off the backplane on version 1 of the CPU. In the first version, I think version 2.0, maybe 2.0A of the CPU, before that reset started showing up. So if you want to use this on any of those boards, you need to make sure that your reset is getting off the backplane and to these chips. You know, you can just plug everything together, and you can use an ohm meter to make sure that it's getting to this point right here at 15, or you can turn everything on, put a voltmeter on this pin up here. This is pin 35 of the 8255, and make sure that when you press the reset button, you get a reset on that one. Because if you don't have that reset connected, this is going to float high, and so the USART and the 8255 are going to stay in reset. This onboard homebrew port and the expansion port will still work, of course, but those two guys will be perpetually in reset until that is there. The last thing on this comes back to this transceiver for the direction for the A equals B, and you can see that this logic here, in addition to decoding when each of these devices are being used, this one also determines when anything on this board is being read. It reverses this transceiver, so instead of going from the address data bus on the backplane to the board, it reverses it so it's going from the board to the backplane to drive whatever's on the backplane. There's also a little board select LED, but that's this LED down here. You're not going to see it turn on. You will see it flicker if you are doing, quick, repeated access of this board. And so it's just really used as a diagnostic to make sure that you are accessing this board. But normally, in normal operation, if you're just doing a I/O now and then, you're not going to see that turn on. It requires repeated, quick access. Or when you're single-stepping the bus, you will see that turn on and stay on for a while. Last thing we're going to address is some people wonder why I use A8 and A15 for the address on decoding some of my I/O. And when the 8085 puts out, either you do an out instruction or an in instruction, it takes that 8-bit port address and it puts it out onto the upper byte of the address, and then it also puts it out onto the lower byte of the address during the address portion of that, because remember the lower byte is multiplexed, either the data or the address. So during the first portion, it puts it out on the upper byte, it puts it out on the lower byte, and then with the ALE, the address latch enable, that is latched to become the low byte of the address. The reason I typically use the high portion, and that's simply because this is set up and held even if the lower address isn't latched for some reason. All right, well that should be enough to get you going on this. I am working on the user's manual. In the user's manual for this board, I have some examples on how to get it up and going, how to do some testing with just the homebrew port, how to run the 8255 in a mode 0 output, how to output a few characters from the USART out to the RS-232 port. All right, well that's just what I wanted to show you on this. If you have any questions, let me know. If you have any feedback about the board or on the user's manual or anything like that, let me know. I appreciate any feedback. All right, thanks for watching, and I will talk with you later. Bye-bye.